Let's finish up the Chapter 18 practice problems. So in this one, it's asking for the energy stored in this capacitor right here, and it's given us C1, C2, C3, and V initial. The labeling is kind of weird in this picture that I got, but this whole thing just means the potential difference. So I redrew it here as just a regular battery, and I wrote right here delta V. So that 18 volts is just a potential difference. So we look at this, and we know that we're asked for energy, so you might be thinking, well, for energy, I just need to know 2 out of these 3 variables, out of C, Q, and delta V. To find energy, I just need 2 of those variables, and you might be thinking, well, I have the capacitance, I have the potential difference, let me just plug them in to this equation right here, UE equals 1/2 C delta V squared. And that's it. But please don't do that, because this delta V is right here. It does not apply to C2. So only way to do this is to simplify the circuit and then work backwards. So we look at this circuit, we see these two capacitors 2 and 3 are in parallel. So we redraw the circuit, and we now have to the right here C23, which is 2 and 3 have been combined to form C23. C1 hasn't changed. 2 and 3 were in parallel to get to C23. So that means that in parallel, we just add the capacitance. C23 equals C2 plus C3. 2 is 10, 3 is 20, so that's going to be 30 microfarads. I like to keep the numbers underneath here so I have enough room to draw my circuit again. Now I'm going to simplify those two, which are in series, to their equivalent capacitor. So that's going to be C equivalent, or C123. When they're in series, then you have to use the 1 over equation. 1 over C123 equals 1 over C1 plus 1 over C23. Parallel to get to this one. So plug in 1 over 15 plus 1 over 30 to get 1 over C123. And you're going to get 1/10. So then when you do C123, find a reciprocal, you're going to get 10. So that's the equivalent capacitance. And now to work backwards, now we know that this potential difference 18 volts here applies to this capacitor. So this delta V123 across this one is 18. So now I'm going to find a charge on this capacitor. I always want to find all 3 of these variables when I'm working backwards. To find a charge, I'm going to use this equation. The capacitance is a charge per potential difference. So the charge on 1, 2, 3 will be equal to the capacitance times the potential difference. So when I do that, I'm going to get 18 times 10. I'm going to get 180 microcoulombs. So then usually I would do this work right underneath here. I just didn't have room. And now I work backwards. I know the charge on this capacitor. I know that these 2 capacitors were in series to get to this one. When capacitors are in series, the charge on them is the same. as the charge on the equivalent capacitor. So now I know that the charge on this capacitor over here, the charge on 2, 3, is the same as the charge on 1, 2, 3, because they were in series to get to that one. So now I know this is 180 microfarads. And now I can find the potential difference across this capacitor, because I always want all three variables. Potential difference across this one using this equation is going to be Q23 over C23. So I'm going to plug in 180 divided by 30, the micros cancel out, and I'm going to get 6 volts. 6 volts for that potential difference. So you can see that we really could not say that it was 18. It's only 6 across this one. And now when we go back one more time, these two, number 2 and 3, were in parallel to get C23. When capacitors are in parallel, the voltage across them is the same. So we know the capacitance of number 2, which is 10, and now we know that the voltage across 2 must be the same as the voltage across 2, 3, because they were in parallel. So it's that same 6 volts. And now finally we have enough information to get how much energy is stored in C2 when we see that we have a potential difference of 6 volts across it, not 18, and we have a capacitance of 10 microfarads. So now we can use this equation that we wanted to use earlier, and we just happen to use this one because we happen to have those two variables. You can look at the equation sheet, and there are other equations you can use. If you happen to know the charge, you can use a different equation. So I'm just going to plug these numbers in here, and that's how I get my 0.18 times 10 to the negative 3, or 0.18 millijoules. Let's do the last one to finish up here. So this one says that we're creating a very large capacitor, and we're given the area of the plates. We're given the dielectric constant kappa that increases the capacitance. It says right here that it has a thickness of 1 millimeter. How much electrical energy would it store if you had this much potential difference across the plates? So the fact that the dielectric has a thickness of 1 millimeter, what this means is that in between your two plates of your capacitor, that you have this dielectric, this material, this insulating material, which they're using paper, that has a thickness of 1 millimeter or 0.001 meters. So we're going to have to assume that that's going to be the distance between the two plates, because the dielectric is going to fill up that whole space in between the two plates. So that's going to be our D. And then we have the permittivity of free space. So first thing we can do is calculate the capacitance using kappa times epsilon A over D. And once we have this capacitance, unfortunately I did not get numbers, but now that we have capacitance and we have the potential difference as 5,000 volts, then we can use the same equation that we used in the previous problem, that the energy stored is going to be 1/2 C delta V squared. Plug in the capacitance that you get from here, and the 5,000 squared times 1/2, and you should get 0.41 joules.